Hello, welcome to the Anritsu Broadband 220 GHz VNA Measurement Technique presentation. This presentation describes how the VectorStar ME7838G broadband system can be set up to make on-wafer measurements sweeping from 70 kHz to 220 GHz. The presentation is provided in 3 parts, and so this is part 1 of the 3-part series. This is the outline of the 3-part series on performing broadband 220 GHz on-wafer measurements. For this part 1, we'll discuss the basic broadband system, the structure and layout, and how we put together a system that can sweep continuously from 70 kHz up to 220 GHz. We'll then go into a bit more detail on the module interface technologies and then discuss the 220 GHz probes that are connected to the module. For part 2, we'll go into more detail about the calibration choices that we have for on-wafer measurements and then discuss some of the best practices when putting together a system for this type of measurement. And for part 3, we'll go into more detail on instrument attributes that are important in setting up a stable and accurate measurement, and then talk about some of the calibration accuracy and repeatabilities that we can achieve with this system, and then finally provide some comparison and examples of measurements. So this is the basic configuration of a broadband VNA system. We start off with what we call a baseband VNA, which is the VNA that operates up to the frequency limits of the test port connector, which for the higher frequencies will typically be a 1.85 millimeter test port. And so the 1.85 millimeter or V connector test port will limit the baseband VNA to 70 gigahertz. So then when the industry wanted to go to higher frequencies in order to do device characterization over a very broad frequency range, we wanted to combine the WR10 waveguide modules with the baseband VNA in order to sweep up to the 110 to 125 gigahertz range. And so in order to do that, we included a millimeter wave test set, and the test set distributes the RF and LO signals from the baseband VNA to the millimeter wave modules. So in the first round of broadband VNAs, the WR10 waveguide modules were used and combined with the baseband going through a 1 millimeter test port gave us the ability to go up to 125 gigahertz. So now we can take a closer look at the structure of a broadband VNA system. And you can see that we're basically trying to combine 2 VNA systems, the baseband VNA and the millimeter wave VNA. And in the baseband VNA, we have our internal sources, LOs, etc. And we're multiplying up the frequencies to the microwave regions. And we have internal downconverters that will downconvert the signals to the IF frequencies for IF processing. And then in the millimeter wave modules, we're using those same sources and LOs for the multiplying up and downconverting back to the IF frequencies within the modules. And so the method that we use for combining these 2 systems is important. And if we use something like, for instance, switches, those switch losses could have an impact on the overall system performance. and end up with degraded performance such as raw directivity, etc. And we'll take a look at that a little bit later on. So in this diagram, you can see that what we're doing is we're taking the signal from the test port of the baseband and running it through the main transmission line, creating a DC path from the baseband to the test port of the millimeter wave module. And so what we're doing is coupling the millimeter wave frequencies to the main line transmission line of the module, as well as using couplers to sense the test and reference signals and mixing them down to the IF frequencies. And so by using couplers, we are trying to maximize the system performance. So we'll take a closer look at some of these aspects, but first we want to take a look at the LO distribution and how they're used to downconvert the millimeter wave frequencies to IF frequencies. We mentioned that the microwave and millimeter wave frequencies are downconverted to the IF frequency for further conversion. What we often use in broadband systems are harmonic converters for this downconversion process. And so we use LO sources as the triggering mechanism for that downconversion. And since a sinusoidal waveform is not necessarily the best choice for this triggering, shaping the LO waveform is one way to improve on conversion efficiencies and linearities. And so in the VectorStar system, what we use are nonlinear transmission line technology that is used to shape the waveform, and the resulting pulses are then used to drive the harmonic sampler. So it's the NL-TL modules that are the millimeter wave modules using the triggering mechanisms for the downconversions within the module and close to the test port. Another aspect for improvement of performance is to operate the LO source at higher frequencies, and so using frequencies up to 220 gigahertz will help reduce the image noise. This would be a good time to start talking about some of the system attributes that contribute to measurement uncertainties. And just like a typical VNA measurement at microwave frequencies, the same concerns about calibration, correcting the system errors such as directivity, match, and frequency response apply to a broadband system. And so the calibration process does correct for some of these system error models, but they will leave some residual levels of error as a result of other aspects within the calibration process. But the general aspect of frequency response, directivity, and match can be corrected for in the broadband system during our calibration process. And so you see that we also will still have additional uncertainties as a result of things like drift and noise and other aspects that are not corrected during the calibration process. So we want to start taking a look at some of the major contributors to measurement uncertainties. Raw directivity is the uncorrected system directivity, and it's a leading contributor to measurement instability. During the calibration process, the measurements of the calibration standard include both the calibration standard as well as the systemic errors. And since the calibration standard is pretty well defined, the calibration algorithm can extrapolate the error vectors and minimize them during the DUT measurements. So in this example, the calibration short is a good way to isolate the directivity vector. And so during the measurements, the calibration correction reduces the contribution of this directivity error for an improved effective directivity, for improved measurement uncertainties. So as long as the phase relationship between the measurements and the error signals remain intact, then that calibration correction remains quite valid. So one thing we want to start being aware of is the degradation in calibration and stability performance of a broadband system when you start adding test port cables between the test port and the coupler. So by adding the cables between the test port and the directional device, this results in degrading the raw directivity. When you consider the fact that adding any kind of a loss between the test port and the directional device, you're attenuating that signal twice the insertion loss of that path. So the directivity error magnitude remains constant, but the measured signal is attenuated. And if the loss in that network is enough, it can reduce the signal level of the measurement to below the magnitude of the raw directivity. So now any kind of flexing of the test port cable or changes in the temperature after the calibration will change the phase relationship between the measured and directivity signals, and thus you're going to start diminishing the effectiveness of your calibration corrections. And so when you have poor or negative raw directivity, these small changes in that signal phase can produce quite large phase changes between those two signals, and thus it results in a significant increase in measurement uncertainties and in instabilities. So getting back to the architecture of the nonlinear transmission line modules, we see again that there is a DC path coming from the baseband VNA through the module to the test port. Now the source signals up to 54 gigahertz are provided by the baseband VNA, and then the test and reference signals below 30 gigahertz are sampled and converted in the baseband VNA. So the architecture of the nonlinear transmission line module combines the source and receivers to the main transmission line through the substrate couplers. And in the NLTL module, the harmonic samplers convert test and reference signals to the IF from 30 gigahertz up to actually 226 gigahertz. And so locating the test and reference receivers close to the DUT optimizes system performance for things such as raw directivity. Also note that the location of the on-wafer probe is attached directly to the test port of the module, so we don't need a test port cable to connect between the module and the module test and reference couplers to the probe, and thus again maximizing system performance. So now we can see the interface between the module and the probe, and going back to our initial description of broadband systems and how we went from a 1.85 millimeter test port in the baseband VNA that can operate up to 70 gigahertz. We then went to a 1 millimeter test port connector in order to go up to the 110 and 125 gigahertz frequencies. We now need to go to an even higher frequency, and therefore we need an even smaller coaxial connector. We need to have a coaxial connector because we're, after all, trying to get down into the low RF frequencies, down to 70 kilohertz in this case. And so designing a connector that can propagate the frequencies up to 220 gigahertz without moding is an important aspect of the design of a broadband system that operates above 125 gigahertz. And we have previously introduced a 145 gigahertz system, which uses a 0.8 millimeter connector. But now we need to go even smaller than that. And so in terms of the outer conductor diameter, we're now having to go to a 0.6 millimeter geometry in order to propagate the 220 gigahertz without moding. So you can see that the inner center conductor is even smaller, and it's actually below the 0.4 millimeter dimension. And we have a coaxial connection then that is both male and female, and the aspect of a male-female means that you need a springing mechanism to mate between the two in order to get good repeatable measurements, good repeatable connections over a multitude of connections. And so we have a female center conductor, but we found that trying to slot the female center conductor was pretty difficult, and especially in terms of providing longevity. And so we ended up doing a slotted male pin, and that has proven to be quite durable and repeatable over many connections. And so we do have a male to female center conductor mating, and the next aspect of a coaxial connector is how do you align the male and female center pins. And so we did explore the threaded connection approach, but we found that wear of the threads can result in misalignment after just a few connections, and we therefore looked for alternative approaches and came up with the use of a UG387 flange, which is a waveguide flange dimension with tolerances that are made for 220 gigahertz operation. So it will give us the repeatability and the alignment, the consistent alignment that's needed in order to make this measurement. So even though the interface flange looks like it's waveguide, it actually is a DC path coaxial connection interface. And so here we see the installation of the system. We have the baseband VNA and the test set that you can see behind the probe station. And then we have the millimeter wave modules mounted on bracket holders, positioned by positioners. And then we have the probe directly connected to the module. And so you see that there are no cables between the test port of the module and the probe. So again, that's going to optimize our system performance. And so these probes are from MPI. They are the Titan series probes, and they are available in 50, 75, and 100 micron pitch. And so you see that a small compact millimeter wave module has a lot of flexibility in terms of installation, but it also makes a tightly integrated system so that you can achieve your optimum system performance in terms of dynamic range, raw directivity, and overall stability. So the broadband probe utilizes a 3D MEMS technology that is well established for measurement applications up to 110 gigahertz. And the MPI Titan probe tips were then scaled and further optimized for the frequency range up to 220 gigahertz. The width of the probe contacts were then also reduced to 15 microns. The shape of the 3D tip provides an easy way to monitor the probe contact point under the microscope. So adjusting this probe on the DUT contact pad is very straightforward. So even inexperienced system operators can accurately position the probes on the DUT pads, and as a result that gives you high repeatability of the measurement data. So in addition, the smallest available probe contacts enable multiple touchdowns on the same device and allows for measurement ability of sub-millimeter wave devices that have very small pads. So the good tip and contact visibility improves the repeatability and reproducibility of the measurement results. And so the system calibration will also be demonstrated to be quite repeatable as well. This concludes part 1 of the 3-part series on the presentation of performing broadband 220 GHz VNA on-wafer measurements. Please continue to part 2 for continuation of the presentation. Thank you.